Hi, this is Mr. Manley. In this video, we're going to solve a system of equations, a linear system with 3 variables and 3 equations. But in this case, we're not going to get a single solution. We're not going to get a unique solution. And if you think about what's happening with these, when we had 2 variables, we had lines like this, right? And we intersected in a point. What's happening with 3 equations is it's not a line. An equation in 3 variables is a plane. And of course, this plane extends infinitely in all directions. If you can think about that as 3-dimensional. So we could be having an intersection of 3 planes in a single point, but it's also possible that we have an intersection of 3 planes and they all intersect on a single line. And I'm not going to try to draw that. That would be too difficult and beyond my artistic skills to do that. But if you can imagine that, 3 planes that intersect on a single line. And that's what we're solving here. So let's just take the first 2 equations and combine those. And then we'll take, let's see if I need to use the 3rd equation. Yeah, I'll take the 2nd and the 3rd equation and combine those. Combining the first 2, I'm just ready to eliminate the x, right? Because I have negative x and x. So I'll just add those 2. And I entered this variable wrong here. That is a y, 2y that I want there. And then adding those, I get y. And then adding the z's, I get minus 4z. And that's equal to 3. Okay, to eliminate the x in the other pair of equations, I need to multiply by 3. And then we can see that the x will 0 out. 3x plus negative 3x is 0x. Negative 3y plus 4y is y. Negative 3z minus z is minus 4z. And then 6 minus 3 is 3. And then what would the next step be? It would be we would combine these 2. So let's just say that I'm going to take this one and I'm going to bring it over here. Combine them. Linear combination. And I can see that the y variable matches. So in this case, I would subtract the equations. In other cases, we've seen the coefficients are opposite. So we added them and they zeroed out. But in this case, they're the same, not opposite. So we subtract them to zero them out. And I get y minus y is 0. That zeroes out. And I've also got negative 4z minus 4z is 0. That zeroed out. And 3 minus 3 is 0. That zeroed out. They all zeroed out. When I see that, that means that there are infinite solutions. And as I said near the beginning, it means that the 3 planes that are represented by these equations intersect on a single line. So what do I do with that? I have to choose a variable to solve for. Now, since the y is sitting here by itself, I'm going to choose the y. I'm going to solve for the y. So I'm going to say y is equal to 4z plus 3. Now, I could use either variable, but I just use the variable that is the most convenient. Will there always be a coefficient of one variable? No, maybe not. hopefully. And then that'll be an easy choice, and that'll be the one I solve for. And then here's what we're going to do. All right, I'm going to erase this. And I'm going to start building my solution. So my solution here is y. And then the z part of my, I'm sorry, that is not my solution. My solution here is the y part. All right, so we have an x, y, z part of the solution, right? So we have an x part, a y part, a z part. So see what I have here? It said y is equal to 4z plus 3. So I've got the y part. The y part is 4z plus 3. 4z plus 3. That's what y is. And if I'm going to say that y is 4z plus 3, then I'm just going to use z for z. So whichever one you choose here, whichever one you choose down here to solve for, you're solving for that part of the solution. And then whichever variable shows up here, that variable is itself. We're going to use that variable. So I'm solving this system in terms of z. And then the next step is to plug these all in. And I can plug into any one of the equations here. This is, again, it's a back substitution set, a back substitution step. Back substitute. So I'm going to back substitute what I've got. I think the second equation looks most convenient. Not looking too closely, but just at first glance, I'm going to use that one. And then I want to continue to solve. What am I missing? X. I want to continue to solve for x. So let's simplify this. X minus 4z minus 3 minus z equals 2. And then I've got x minus 5z minus 3 is equal to 2. And finally, x is equal to 5z. And we'll add 3 to both sides and get plus 5. So there's, and I wrote that z, x as a z, or the z as an x, so that's z. And that's it. X is 5z plus 5. And that's the x part of our solution. 5z plus 5. And then we're going to make a statement. We're making a statement here that we're solving in terms of z. And that's a choice. We could make other choices. I could have a solution, and the solution could look like this. I could have a solution that has, I'm going to use y. And then z is going to be in terms of y. And x is going to be in terms of y. So notice that we're ending up with z, z, z. The solution is in terms of z. And that was just the most convenient thing to do because I had this y here that was easy to solve for. Now look, if I solved for z, it's just not as convenient. So if I take this one and I solve for z, what do I get? I get negative 4z is equal to 3 minus y. And then I'm going to divide by negative 4, divide by negative 4, and I get z is equal to, I really don't know what else to do, but just leave it like that. I mean, I could do some sort of manipulation here, but you see, that's just really not very convenient. But that's what z is in terms of y. So that's 3 minus y over negative 4. All right, we're fine up to that point. But now look at the next step. The next step is a little bit of a bear, right? I got to give myself some room over here to do another back substitution, which I'm probably not going to complete because just unnecessary. So what would it be? I would know what y and z are, and I need x. So say I want x minus, and then y, x minus y, minus, and then this guy here for z, (3 minus y over -4, equal to 2. So I substituted into this equation this value of y and this value of z. And then what do I do from there? I solve for x. That's a little bit of a pain, isn't it? I'm going to have to say x equals what? And I'm going to have to work with this messy expression here. So I'm not going to do that. And what you want to do is you want to try and solve for the convenient value and use that one. But understand that we could solve for any of them, for any of the 3 variables. So I showed you, I did the complete solution for z. I showed you part of the solution for y, and understand that we could do it for x as well. I could have x, and then I could have y in terms of x and z in terms of x. Okay? So that is solving a system of equations with infinite solutions.